All right, good morning. Let's see, a couple of things we're going to talk about today. Number one is we're going to talk about the project. And number two, I'll return the midterms. We graded them yesterday, and I'll discuss this in a minute. A little bit what, I'm going to walk over the exam a little bit and what the type of things is that you had to look at. I think we posted the solutions already online yesterday evening, so you should have access to them as well. But before doing so, what I'm going to do is wrap up first my discussion of the inverter. Then we'll take a break, talk a little bit about midterm and project, and then we're going to go back to the inverter. So also in order to accommodate the project, which you will actually get a full description. We're going to launch it probably tomorrow evening, Friday morning, and you get a full description of what you have to do. It's going to be a project in 3 phases. But in order to get you jump-started, I'm going to reshuffle the order of the lectures a bit. And the next 2 lectures are going to be about arithmetic. We're going to talk about how to do logical computations. And then I'll also insert a lecture on memory elements, because that's going to be important as well. So we're going to move that a little bit forward into the sequence of the lectures for the semester. I think it's going to be quite a bit of fun. The way I look at it, it's not going to be easy. Let's put it this way. It's a fairly hard problem to do good. We'll walk to that in a minute. Okay. So, oh, by the way, labs, we have the last lab this week. So for you, there's one more session tomorrow, and that's it. So you should have the skills now to be able to start rolling and start doing design for real. Kind of basically getting your design to roll. Okay. So as I said before, I'm going to talk about projects and things like that. I just want to wrap up where we left it off. There's a couple more things I want to say about the inverter voltage transfer characteristic based on real transistors, not on this switch model we have been using so far. And what I walked the last class is that if you would like to the real problem with determining the VTC is a large-scale analysis with nonlinear devices. So the key challenge at any operational point is to determine what operation mode each of the transistors is, because that's going to determine the equations you're going to write down and what you have to solve. So the solution basically is quite simple. Well, it's not simple, but it's if you do it methodologically right, it actually becomes quite simple. You have your circuit, you have a set of inputs. Based on the inputs and maybe some pictorial picture like I show here, where you do some graphical type of analysis. Based on those, and putting those together, you can get an idea of what operation mode your transistor should be in or may be in. So you make that assumption. You write down assumption 1 is transistor 1 in saturation, the other one linear, ALF, whatever. You write down the equation, solve it, and then you get an answer. And once you get your answer, then you can check if your assumptions were correct. Okay? So that's very important that you do that. Always check, because otherwise you might get very bizarre results. So, like what I showed here is that by manipulating the voltage, the IV characteristics of the PMOS and the NMOS of the inverter, I can put them on top of each other, and now I can start getting an idea for different input values. These are the red dots, where the different transistors might see from an operational perspective. Are they basic? Like for instance, if the input is low, we know that the NMOS is going to be off, the PMOS is going to be in linear mode. And then if we start increasing the voltage, then we gradually turn on the NMOS, which is going to be in saturation at that point in time. The voltage over the NMOS, since the output is at a point in time, if Vin is low, the output over the NMOS is going to carry a very large voltage, and as a result of that is going to be in saturation, while the PMOS carries a very small voltage over the drain to source, so it's going to be in linear mode. Like for instance, that's this particular operational point. And then you move on, input rises, we see the operational point move gradually but surely in such a way that at some point in time, the PMOS is going to saturate. And at that point in time, we have both PMOS and NMOS in saturation, very flat curves, kind of very sensitive to a little change in Vn, high gain. That's a high gain region of your inverter. And then finally, the voltage drops, and at a point in time, we see that our NMOS is going to move into linear mode, while the PMOS remains saturated. And finally, the PMOS is turned off. Okay? So that's kind of the characteristic. So based on this, I can plot my voltage transfer characteristic, and for each of the regions, I can start making assumptions what the operational modes of my transistor is going to be. So for instance here, if I want to solve the gain, for instance, in the middle, well, you have to write down the equation for your NMOS in saturation, your PMOS in saturation, and you say that IDN is equals to minus IDP, where this is the drain current of the NMOS, drain current of the PMOS. They have to be equal in steady state. That's always the case. It is a DC analysis. And we write down the equation in saturation and we solve it for V out versus V in. And bingo, we got that. And you can then find the gain. You can take the derivative and you figure out what the gain is in this particular point. Similarly, we can do the same thing in the VIH and VIL regions. There you see that we typically will have the NMOS in saturation, PMOS in linear mode for the VIL, and for the VIH it's just the opposite. Okay? So that's doing that. Then you can solve it, then you find your voltage transfer characteristic. For instance, I can actually find the point Vm. One of the important ones, remember the switching threshold is the point where V in is equal to V out. That's a 45-degree line. If you go back to the previous one here, that's the Vm point. If I want to solve for Vm, what is Vm? Well, I notice that NMOS in saturation, PMOS in saturation. I write down my current equation and I will replace both V in and V out by Vm. And I solve it for Vm, which is not a simple equation. It's a fairly complex equation when you get it. You write the equation down, this is what you approximately get, and with some simplification, we can come up with an expression for Vm. Rather than doing this by hand, you might throw it in MATLAB or whatever, might find a solution, and you find a very nice curve of Vm as a function of the PMOS versus NMOS ratio. And remember what we talked to you before, you say if you want to have your switching threshold in the middle, I have to make my PMOS equal strength as my NMOS. And that's exactly what it shows here. This is 2.5 volt supply voltage, the middle point is around here. This is where we're going to have WP over N. This is approximately where we're going to have an equal strength. It means that we have to make our PMOS about 2 to 3 times stronger than our NMOS. Okay? And then if I make, very important to observe also, is I make my PMOS stronger, my switching threshold is going to go up. You can kind of imagine that, right? If I have, considered again as two resistors fighting each other, if I make my PMOS wider, I reduce the resistance of my PMOS device, it's going to be stronger in pulling up, my middle point is going to move up. If I make the NMOS stronger, I'm going to move the switching threshold lower. Now you might argue, why would you ever be worried about that? Remember, the ideal gate is where PMOS and NMOS are equal strength, symmetrical characteristics. But later on in the semester, we'll see some examples where actually it might be advantageous to move the switching threshold up or down so that you get better noise margins in one direction or the other direction. So remember that. I want to basically switch the threshold upwards, make your PMOS wider, you move it downwards, you make the NMOS wider, which is also obviously going to impact your logical effort, as you might imagine. Okay, so VIH and VIL. So we have VOH, we have VOL, we just decided VM. How would you find VIH and VIL? Well, I'll show you one example here, but what would you typically do to find VIH? So I have my voltage transfer characteristic here. How would I go along typically to find VIH and VIL? What would be the strategy if you would follow the general procedures?
You could look at the gate voltages where one of the transistors would turn on.
Right. So, yeah, it's the same thing, right? Well, it's not really turn on. What's the definition of VIH and VIL?
The slope equals -1.
That's right. Slope -1. So let's look here at approximately this point here. I would say this is approximately -1 at 45-degree line. So we might imagine that in this operational region, the NMOS is going to be in saturation, the PMOS is going to be in linear mode. So again, what I could do is write IDP, or minus IDP equals to IDN, or IDN plus IDP is equal to 0. I have VI and VO, input and output voltage. I can write down those currents and write down this expression. In order to find the VIH, or in this case the VIL, I'm going to say that what I want to do is take, if I have this expression here where I express VO as a function of VI, what I'm looking for is a point where the derivative of VO with respect to Vin is going to be equal to -1. So first step, write down your current equation. You have an expression of VO versus Vin. You have to manipulate it a bit so that you bring VO explicitly outwards. And then you take the partial derivative or the derivative with this VO with respect to VI, and you get the gain factor. And you solve it. And that should basically give you VIL. Okay? For VIH, the same thing, but now for opposite operational modes. In this case, the NMOS has to be in resistive mode and the PMOS in saturation. Now, this is fairly complex. I can promise you that when you start writing down the equations of a transistor, you will see you get a very long expression. So what I will do, and long expressions are kind of cool. They fill a lot of paper, but it's very hard to understand what the trends are. Ultimately, yes?
I'm sorry, I didn't cut you off. The VIL, what was the L on there?
Right.
Just the subscripts.
So this is VIL is here, right?
Oh, in low, I'm sorry.
Yes, in low. And VIH is in high. Okay. So, the reason I'm finding those expressions, like the one I just showed you here, why is this impression worthwhile to basically deriving? Why not just do it graphically? Why not do it with SPICE? Well, the advantage, at least, if by looking at expressions like this, you can see what's happening you can see some trends. What happens if I change parameter 1 or parameter 2? What's going to happen with my voltage values? So it gives you insight. But if you have a very complex expression, you don't get any insight. You want to simplify it. Get the basics in there, the basic trends that you can understand what is going on. And that's why doing the VIH and the VIL with the derivative, and you get this long expression, is going to be really hard to interpret what's going to happen if I want to increase noise margins and so on and so forth. So that's why we simplify the approach a little bit. Let's go for simple expression. And a simple expression would be as follows. If I would assume that I have high gain in the middle, and have a decent gate, not a really degenerated gate, but a decent gate with a decent VTC, actually a good approximation of the voltage transfer characteristic is I can find Vm, and I find the gain in Vm. Okay? So if I know what the gain is in Vm, that's easy. Once I have Vm, you take the derivative, you have the gain. G. Let's call that G. Then if I assume that in the whole transient region I'm going to have the same gain, I just extrapolate it upwards and downwards. And then the cross points between the VOH level and the VOL, I say, this is really where VIL and VIH will occur. It's a crude approximation, but actually it's not too bad, because in reality, what you will get is something like this. Right? That's your voltage transfer characteristic you might get. And then you see that your VIH and VIL points might not be that far away from this approximation. So the beauty of this is that once I know Vm and the gain factor, and I know VOH and VOL, I can determine VIH and VIL. So there's only two parameters in here, Vm and the gain. Because once I know the gain, I can easily find out what the value of this point is or of this point. Like VIH is Vm minus Vm over G. That's Vm over G is the gain factor over the Vm. And the same thing here. And you can find the noise margins. So again, like always, if things get too complex, simplify, make an assumption, and then obviously later on you check if your assumption was a decent one. In this case, actually, it's pretty good. The gain I discussed about the gain before, and I just want to show you this, what's happening with the gain and why this is a decent approximation. If you look at this is an inverter, 250 nanometers, 2.5 volt supply voltage. Look at the gain here in the middle. If I take the gain and extrapolate it out, I will get something like this. My 45-degree lines are approximately here. So you can see that in this case, when the gain is really high, I might have somewhat of a, I would say, optimistic view on my noise margins. Because in reality, my noise margins are a little bit smaller here. So it's somewhat of an optimistic approximation. But you will see that if you go to lower and lower values of the voltage, actually, the approximation is pretty good. The other thing what it shows is, what I'm doing here, actually, this is, what I'm showing here is your voltage transfer characteristic of your gate as a function of the supply voltage. So this is an inverter in a given technology. I'm not changing anything. I'm just scaling the supply voltage. 2.5 volt. This is 1 volt. 1.5 volt right here. From here to here. Still a very beautiful inverter, right? Perfectly fine, nice voltage transfer characteristic. I go to 0.5 volt, and I still get a very nice voltage transfer characteristic. I still get decent gain in the midpoint, which still gives me a very nice and beautiful voltage transfer characteristic. Which shows actually something interesting, that actually I can take the supply voltage of an inverter and I can start dropping it and it stays an inverter. Even if the voltage gets very close to the thresholds. Like in this process, the thresholds are what? About 0.4? And I'm operating supply voltage at 0.5. Which means that my transistors are barely on. It's quite amazing, isn't it? Why do you think that still could work? Why do you think actually, turns out if I go lower than the threshold, like here, 0.2 volt, I still get an inverter. Quite impressive now. I'm basically operating my devices at voltage which are below the threshold. They never turn on, and I still get a voltage transfer characteristic which is quite beautiful. Actually, there's a decent gain. It's not as good here. Here I have a gain of about -20 or something like that. Here the gain maybe -5 or something. But still enough. So why would it work? Why do I still get an inverter while my transistors are off? They never turn on. Strange, isn't it? Any guess? Yes?
Maybe it's because they never really turn on? Or?
Yes, that's obviously true. Because if they really would be turned off, nothing would happen. Right? That output would be floating around there, and nothing would happen. So you're in the right direction. They never really turn off. What does that mean? Typically, a transistor, when you're below the threshold, it should be turned off, right? Sorry? That's right. It's current leakage. On my transistor, we haven't really talked about that. When we talked about the inverter, we said below the threshold is a point where we turn off the channel. In reality, below the threshold, there's still current flowing, leakage current, drain to source current. We'll come back to that later. But now you can imagine that you have two devices on top of each other that are leaking. They have leakage current flowing. But you can imagine that depending upon the voltage, one will leak more than the other one. So the operation of this inverter here is actually fighting, leakage currents fighting each other. If one leakage current is larger than the other one, it goes down or up, and you get a voltage inverter. Now this sounds kind of an iffy up proposition, something you don't want to do, but actually it makes sense in certain circumstances. This is not going to be fast because it's leakage currents, right? Charging and discharging a capacitor with a very small current is going to be hard. So it's going to be slow, but it's going to be low power because I'm switching things not over many volts, but actually only over 200 millivolt, or maybe even lower than that. So for some applications, like this thing, watches don't do very much. They have to decide every second they have to move the second arm, and every minute they have to move the other one. So not rocket science computation going on, but still you want to have your battery in the watch going for a couple of years. So all those things are operating in subthreshold region, as we call it. So remember, you still can operate a circuit below the threshold voltage if you really want to do low power design. Ultimately, if I keep on dropping the supply, you can see what's happening with the gain. Finally, my gain starts degrading. And this is for about 50 millivolt of supply voltage. I still get kind of a characteristic, but it's not very good anymore. My gain actually drops to -1. So you have no VIH and no VIL anymore. You have no 1 and 0 region. At that point in time, you're done. Remember, for a digital gate to operate, the gain in the transient region has to be always larger than -1. Otherwise, you don't have a gate. So this is actually the minimal operational volt of this inverter is 50 millivolt approximately, which is kind of astonishing that you still can do logic at 50 millivolt. All right, so that's important. The other thing to remember, I already mentioned that, but if you look at your voltage transfer characteristic, this is a beautiful inverter, very nicely sized. You can see that for the black curve, the nominal curve, my midpoint is exactly 1.25 volt, purely symmetrical. Now remember what I said about changing the transistor ratios? If I make my PMOS wider, what happens? With VM, goes up, right? PMOS wider, the resistance of the PMOS gets stronger, it pulls up the VM. And you can see that happen right here. If the NMOS is wider, I'm pulling down my VM, and the VM will basically go to somewhere up here. So I can manipulate VM by changing the PMOS versus NMOS. What you're really doing is shifting your voltage transfer characteristic to the left or to the right. If I make it NMOS wider, I move it to the left. If I made the PMOS wider, sorry, it was not perfectly correct. It should be like this, actually. That's more accurate. But I'm moving my curves to the left or to the right. Okay? Something else may do this. Actually, this is what you do as a designer. As a designer, I'm going to be very meticulously determining where my PMOS should be and my NMOS should be. And I figure out what my VM is and where my characteristic is going to lie. However, there might be other things that make your voltage transfer characteristic switch. Things that are beyond your control. As a designer, we typically assume that I give you a SPICE model. And you believe that the SPICE model tells the truth. It does not. Right? A SPICE model is, how do people create SPICE models? Well, you go to a fab, you manufacture some of those transistors, and you measure them. And then you extract all the parameters. That's the way it works. Now, if I fab a second transistor, or a third, or a fourth, or a fifth, and you measure them again, you might not get exactly the same values. It's not such a way that technology is a perfect executional mechanism. It's not. There's a couple of things that may cause your transistors, one from the other one, to change and vary from each other. A couple of examples. Remember lithography. Right? Lithography is the way we define patterns. And you assume that you're going to get exactly the same pattern defined everywhere. That might not be. Depending on where you are in the field of the light, you might have some variations. The way the patterns are printed might be different. And if you think about the threshold, for instance, so that might change your W and L. Might not all be the lithography. I'm doing etching steps. So when I do etching, I put either liquid acids on it, or I use some dry etching using a plasma, which is going to take pieces away. Again, depending on how and where you are, the density, you might see variations in how much material gets taken away. So a line that's nominally, let's say, 120 nanometers might be in one case 125 nanometers, in other case 150 nanometers. So you can imagine that the W and L of your transistors might vary from transistor to transistor, which means also the current. So that's one thing. It's the W and L variation. The other important, very important variation is the threshold voltage. You measure the threshold voltage in one place and you get 0.3, and in another place I might get 250 millivolt or 350 millivolt. You might see variations of up to 50 millivolts in your threshold. Again, why might that happen? Well, if you look at the equation of the threshold, basic equation that we saw, there's some material thing that's not going to change very much. Well, it might change. Because remember, we're implanting. If you basically determine the built-in voltage of a transistor, it's going to be determined from the dopants in the channel. How much dopants do I have in the channel? Or in the gate? Now, if I have a very big transistor, and I say I do a doping of 10 to the 17th or 10 to the 18th boron ions per square centimeter or something like that, sounds like a huge number. If I do a transistor that's only 50 nanometers, actually you can start counting the number of impurities that are going to be present under your channel. Sometimes it might be 17, sometimes it might be 15, because you're starting to go into the discrete world. So one transistor will have somewhat of a different doping profile than the next one. Again, it's causing variations. The bottom line is that definitely when you go to smaller and smaller geometries, smaller devices, variations are becoming more and more important. And your transistors are going to be quite substantially different. Now, I can be a very naive designer, and that's what you typically do. You do your design and you use everything and say, I'm going to use my nominal SPICE model. And you get a result. And then you get your chips back and you see some of them are way faster and some of them are way slower, or some of them might leak more, or some of them might use more power. So the question is now, what are you going to sell? When you have to sell your part, you have to basically give it a certain set of specs. So it's typically the worst case specs that are going to determine what you can sell. Like if I have a microprocessor and I say, well, I want to clock it at 2 gigahertz, and some of them come in at 1.5 gigahertz, and some of them go at 3 gigahertz. Now the 3 gigahertz ones, these are cool. Right? These are really nice. The 1.5 gigahertz we don't like very much. So if I basically sell them all in a batch, I have to sell them as 1.5 gigahertz microprocessors, which is not very good because I'm losing some advantage. So what you do, if you're a company like Intel, you measure them all, and you put different labels on them. You call one the 2 gigahertz, you call whatever Pentium, with some, and then you basically, the 3 gigahertz one, you basically say these are the turbo ones, and you sell them for more, even though it's exactly the same design. So you use variations to create different bins, and you sell them at different prices. That's fine for a microprocessor, you can do that. But if I have a phone, a cell phone, I say, well, this cell phone kind of works occasionally, this one works most of the time, this one works all the time. That's not a very good business proposition. They have to work all the time. So you have to have a part that works or not works. So you have to take into account those variations when you design. So that's very important. Now the way you typically do that is, or the fabs are going to tell you how to do that, is they're going to give you not one SPICE model, but they give you for every transistor 3 SPICE models. So for the PMOS transistor, I will have what's called a nominal model, a fast model, and a slow model. So you have nominal, fast, and slow. And the same thing with the NMOS. I have a fast model, a slow model, and a nominal model. Now, what I can do now is simulate my part not only with the nominal transistor models, but also with all the 4 corners. Because now what you have is like, you look at PMOS, NMOS space. This is NMOS, this is PMOS. This would be my normal operational point. For the NMOS, I can be fast and I can be slow. For the PMOS, I can be fast, I can be slow. So now we have 4 operational points that you can look at. When, for instance, I can assume here a slow NMOS, fast PMOS, or a fast PMOS and fast NMOS. This is a fast NMOS, slow PMOS, slow NMOS. These are 4 operational points, now extra points. This is the normal one. Then I can simulate my design. I know that my real design is going to be somewhere in that corner, in that square. Because these are the extreme circumstances. The fastest possible transistor, the slowest possible transistors. Okay? So that's what we call corner simulations. And going to determine what the worst case is. Now, think about it for the voltage transfer characteristics. Suppose now that I have a fast PMOS and a slow NMOS. what do you think will happen with the voltage transfer characteristic? I have my normal voltage transfer characteristics, which is the one in the middle. What would happen if I get a fast PMOS, slow NMOS? Yes?
When you say fast PMOS, you mean it bits more current, right?
That's right.
Okay, so it'll shift to the right.
It's shift to the right. Because fast PMOS means that your threshold is probably going to be a little bit lower. Right? That could be the main reason it's fast. I have a lower threshold, which means for the same voltage I get more current. Which means also that the resistance is going to be smaller. It's the same thing as making the PMOS wider, the same effect. So I'm going to pull my voltage transfer characteristic to the right. If I go, on the other hand, a fast NMOS and a slow PMOS, I'm going to move it to the left. And again, that's shown right here. Same effect. So process variations will cause your voltage transfer characteristic to change as well, but also will cause changes in speed, power dissipation, and so on and so forth. So the idea there is that you do these corner simulations. And somewhere in the project, we'll make sure to do that. Now, the other approach is to do pure random. You just randomly select, you have a distribution of the possible values you might get, and then you do a whole bunch of simulations using random values, and you look at how delay varies as a function of VTP, for instance. You get a whole bunch of things here. So here you have high VTP means slow devices, low VTP means fast devices. And you can see somewhere all your solutions are going to be in between that. But if you do a corner simulation, you're going to have a square around that, which is going to contain all the possible values. Okay? So I just wanted to point out that process variation, that you shouldn't be thinking that I'm simulating my thing, I get a number out there which says my propagation delay is going to be 1.27 picoseconds or nanoseconds, and you simulate it and you have 4 decimals. When you get your chip back and you measure it, you're going to be all over the map. So never do simulation, never give me results of propagation delay simulations with 4 or 5 decimals. It's meaningless. If I get 1.2 nanoseconds picosecond, I'm already going to be quite happy. That's more than accurate enough. Okay? All right. Good. So that's the DC characteristics. So the midterm, as I mentioned at the beginning of the lecture, graded yesterday evening. The solutions are online. You should have gotten a message on that. So what I'm going to do is walk you briefly through the solution and give you an idea of what we basically were looking for in each of the questions. So let's return here. If the thing wants to. Okay, go away. Okay, so I think the first question took a number of you by surprise. It's not something that's kind of the typical question that was asked, but it's a good one to understand. Most of you did fairly well. Some of you kind of make it a little bit harder than it should have been, but it really was kind of balancing out, combining 2 factors together. Cost of design is some part that's proportional to the number of chips you have, some part is a fixed cost. And the more parts you fabricate, the smaller that fixed cost is going to become per part. So like in this case, the first one, the NRE, the non-recurrent expenses, was the design, $8 million plus the mass cost, total $9 million, which is going to be shared over 10 million parts. So you divide 9 million by 10 million, you know that per chip, I'm going to pay 90 cents for NRE costs. Okay? Then the other part is how much do I pay per chip for the manufacturing? And there you have a number of components. The first one is the manufacturing itself, the silicon processing. The other one is packaging and test. Every time you have a package, that's a cost per die, and test is a cost per die. So we said that packaging and test costs were about $2 per chip. Okay, so that's a fixed factor, $2. Now, the only remaining thing you still have to determine is the cost per chip. The cost per chip is going to be determined by how much do I pay to manufacture a single wafer, divided by the number of working chips on that wafer. So you first have to figure out how many chips are on that wafer, and then how many chips do work of those particular sets. Now to figure out the number of chips per wafer, there was an expression that I had given in lecture, which computed the number of chips per wafer. You have a round wafer, you have a square chip. So you can compute the area of the wafer and divide it by the number of chips, or the area of the chip, which is 1 centimeter square. So pi times 10 centimeter, by the way, make sure that you use the radius and not the diameter when you compute the area. So a couple of you kind of made a little error there. So it's a 20 centimeter wafer, so the radius is 10 centimeter. So the area is 314 square centimeters, 314 parts. But one thing you have to remember is that not all of these parts are going to be working, because some of them are going to be sitting on the edges. You have a square thing on a circular.
So that was in the 0.85? I mean, non-working chips are physically on a whole chip?
Yeah, they basically are. No, you figure out how many chips do I really get. So you don't even go to 0.85 yet. You compute, here's my area, how many chips do I have maximally? So that's not going to be 314, but you lose a bunch of them right away. With that second part of the expression says the ones that are basically sitting on the edges of the wafer. So instead of 314, you get 270. Of those 270, not all of them are going to work, because I have a yield factor. Yield factor says 85% of the chips work. So you multiply this 270 by 85, 0.85, that gets you the number of working chips. And that's going to determine the cost per chip as the total cost of the wafer divided by the number of working chips. And you add 2 to that, you get 23.8, you add 0.9, and you get 24.7. All right. That was part one. Part two, the goal there was to say that now what we're going to do is just change the wafer size. We have a new fab. Instead of using 20 centimeter wafers, we use 30 centimeter wafers. For the rest, I can reuse everything. I can reuse the masks, and there's no design cost because I don't change the design. So NRE, in this case, the NRE is going to be equal to, let me just go back here. Okay. The NRE in this case is 0. There's no cost for NRE because everything is reuse. No design effort. The only thing that changes is I have more chips per wafer. And the cost per wafer has changed. Instead of being 5K, it's 10K. But now I can compute the number of chips per wafer. It's a larger wafer, so I get 640 chips per die. And you multiply by the yield, the same yield, you get 0.85, 10K. Bottom line is the price goes down from $24 to about $20. Again, we're not really looking at all the details. If middle computing error here and there, we didn't really look at that too much. Quite liberal integrating on this. Okay. Now, the next step. What I'm going to do is take the same design and shrink it. I'm going to move it to a new technology. 65 nanometers to 45 nanometers. Now, one thing to remember. Why do we scale technologies? If we scale technologies from one to the next generation, it's always to make our chips smaller. Same design becomes smaller. And the number we always use, if you do 65, 45 over 65, what do you get? 0.7. 0.7 squared is 0.498. It's half. So your chip gets half as big when you go from one technology node to the next one. So your area gets half, which means that per wafer, I'm going to get a lot more chips. That's the big advantage of that scaling of the technology. And that's really part 3 of the question. Right here is now we're getting about, you use the same equation again, same wafer, but now you have to fill in the smaller area of the die, 0.5. You get about 1,319 chips per wafer. Now, I didn't give you the yield. You had to compute the yield and say use the expression that we had in class, or basically in the textbook also, which computes the yield as the number of defects per square centimeter. And this is the equation. You fill it in, you get 0.79. So instead of 0.85, we have 0.79 as yield. You fill it in, you divide it out, and you get basically the cost per chip is 9.28. There's new NRE with this now because we had to redesign it and we had to make new masks, which were more expensive. So I get basically $0.25 per chip as NRE cost. And total is 9.5. Okay? So that was kind of the gist. I said most of you did fairly well on this question. Some little deviations here and there, but the average on this question was quite good. Last one is, however, the power. This, some of you kind of got a little bit confused here. Power, the only dynamic power, no leakage, CV squared F, right? That's the equation. So what changes? F doesn't change because I told you we're going to clock it at the same clock frequency. So F is no change whatsoever in F. V squared. V squared, what I said is that the new technology scales the supply volt with 20%. So instead of 1 volt, it goes to 0.8 volt. 0.8 volt squared, or basically something like that, is a factor of 0.64 in power reduction, purely by voltage scaling. So what happened with capacitance scaling? And that's where most of you kind of made an error, is that if you look at capacitance scaling, it said the capacitance per unit area increases by a factor of 0.7, which is again typical. If I scale down my transistors, my oxide is going to scale as the other dimensions. So everything scales by 0.7. My oxide thickness is going to go down with 0.7, which means that the capacitance per unit area is going to go up with a factor of 1 over 0.7. However, at the same time, so the total capacitance is equal to the overall area times the capacitance per unit area. So the capacitance goes up with a factor of 0.7, but the area is shrinking by a factor of 0.7 times 0.7. All your dimensions are shrinking by 0.7. So I get 0.7 times 0.7 over 0.7, you get basically 0.7 factor. So your capacitance actually goes down with 0.7%. It reduces. So you get your capacitance is going to go down with 0.7. Your VDD goes down at 0.8 square. So overall, your new power with respect to the old power is going to be 44%, 4.8% of the original one. Or you can say that the power is reduced by 55%. Okay? So that was a little catchy part, is here what's happening with capacitance if I scale down a technology. Okay, that was question 1. Question 2 was kind of a tricky question, but again, most of you did quite well. What we're really saying here in this case is that we have a gate. We take our traditional gates, but we're going to flip the game. We're going to make the PMOS twice as good as the NMOS. Right? That's really what we're saying. So assume that PMOS suddenly have mobility, which is twice as good as the NMOS. It will never happen, but you can dream, right? So what's happened with the logical effort of a set of gates? Well, obviously, now, in order to get a symmetrical gate, I have to make my NMOS twice as large as the PMOS. So we just invert the story. So this becomes 2. Oh, sorry. This becomes 2 and 1. So what's happening with the inverter logical effort? Well, the inverter is always, per definition, a logical effort of 1. That's always the standard. Logical effort of the inverter, 1. The only thing that really changes, ultimately, it's pretty much the thing, but you inverted everything. Like for a, if you look at this gate, the NAND gate here, we have now 2 PMOS in series. This has to be 4, 4. This has to be 1, 1. You get 5 as the low overall input capacity, so your logical effort becomes 5, 3. This was typically what we would see for a NOR gate. Now we go for a NAND gate because we just flipped it around. And the NOR gate becomes like a NAND gate, 4/3. And the same thing with larger devices. So bottom line is what was good in the old technology where your NMOS is better, there you were better off with NAND gates, here you're better off with NOR gates. Okay? And we can do the same thing. Well, okay, let me just get back here. All right. So then we asked you to compute the, have a logical path. There's a couple of inverters, one NOR gate, a couple of NAND gates. You can observe already that this thing is going to be NAND gate dominated. That's important for the last part of the question. There's also a little branching effort in here. So to figure out what the path effort is, you take the product of the logical efforts, which you have solved. We know F is the ratio of input and output capacity, and we know the branching effort is 3, so you get your path effort. And then we just do the usual thing. 5 stages, so the effort per stage should be 5.3, and then you can work backwards from the load and find the sizes. This is fairly standard fare. You should be able to do that in your sleep by now. Okay. So the last part is, as designer, you can choose what technology you can play around. So we gave you the 3 technologies. One was the technology we just introduced. PMOS is 2 times as good as the NMOS. Number 3 is the traditional one, where the NMOS is 2 times as good as the PMOS. And then you have a technology where the PMOS is as good as the NMOS. The question is, which one would you pick for this design that I showed you? Well, it's all depending upon logical efforts. Which one is going to get the better logical effort? So if you look back at the design, you can see here that this design is, inverters don't change. Inverters, independent of the technology, inverters will have the same logical effort. So nothing happens there. So we have 2 NAND gates and 1 NOR gates. And one of them is a fairly large one. And it also has a large fan out. So in this case, it's clearly that you want to get as good a NAND gate as possible. Now, what is giving you good NAND gates is technology where the NMOSes are good. So that's why we picked the third solution, the one where the traditional solution where the NMOS is twice as good as the PMOS is going to give you the best design. Okay? Because it's dominated by NAND gates. Would have been by NOR gates, I would have picked the first technology. And the best way to figure it out, if you're not really sure, write down the logical effort for each case and compare them. All right. So again, overall, the averages on those 2 questions are pretty good, are very good actually. This question was the most tricky one. That's where most of you kind of struggled. Is this design, which is kind of a tricky one, in the sense that it does 2 things. The first one is a gate that has a VOL that is not equal to 0. Okay? The VOL, the low voltage, is going to be 0.2. So I can draw the voltage transfer characteristic. In reality, what I know is that VOH is going to be 1.2 volt. VOL is going to be 0.2 volt. And if you want to approximate when the transistor turns on, just use a switch model. At 0.4 volt, actually we said that both transistors are the same strength, and both of them have a threshold voltage of 0.2 volt. So you can see that the NMOS turns on at 0.4 volt, if you're about 0.2 volts above the ground, which is 0.2 volt here. So NMOS turns on, we flip to the middle, we flip to the middle point, and the middle voltage is equal size transistor, so equal strength. You can approximate this as something that sits at around 0.7 volt, which is the middle between 0.2 and 1.2 volt. It's 1 volt, the middle point is 0.5 volt, 0.2 plus 0.5 is 0.7.
Dr. Ryan,
Yes?
why do we have a plateau for that middle operation?
You wouldn't really, it's an approximation. Remember the switch model? Assume that both transistors are on at the same time. You get a resistive divider. And a resistive divider will basically make both of them equal strength. It brings you to the VM point. In reality, it will be something like this. Right? And there's no real problem if you showed something of this nature too. Right? Now, this is just saying, if you take the switch characteristic to the extreme, you said transistor turns on, you have the on resistance, and the on resistance doesn't vary. Then you fall right away to the VM. And you stay at VM till the other transistor goes off, and you get this kind of staircase characteristic. But the staircase made life a little bit easier for the next steps. Now, if you look now at VM and the output stage here, the output stage, that's a tricky part. That's where the tricky components came in. If you look at this NMOS here on the top and this PMOS at the bottom, what do they do? Well, we know that they're diodes, basically. Can put it, almost look at it as a diode. This transistor, which is always saturated, it's always on, but it never can, you know that from the time the output here goes higher than VDD minus VTH, it shuts off. So you can almost imagine that this is like a voltage source with a value of 0.2 volt, a drop. And the same thing at the bottom, the PMOS is exactly the same thing. It's like a 0.2 volt offset. Because if you go close enough to the voltage rail, bingo, it shuts off and keeps it up. That's really the trick. What we said, every time you have an NMOS pulling up, you lose a threshold. If you have a PMOS pulling down, you lose a threshold. So really this kind of offset voltages.
So like, technically, doesn't it depend on like the starting voltages at the immediate nodes? Like this is why I found the problem. Maybe I don't know how to analyze a circuit very well, and maybe I should have figured this out. But it was
Right.
it was really confusing because it seemed to me that the output characteristics that you would give would depend on what voltage those intermediate nodes started out with.
But remember,
Is that not actually true if you actually are thorough about it and work it all out? Or-
no, actually, it's DC, right?
Okay.
It's a DC characteristic. It says I'm basically going to solve for every particular point in the space. You apply the input, you see what's happening at the output. So there's no, in principle, there should be no input of prior knowledge, of prior activities. So if I put a mid voltage here, you're right that in certain cases, if I put a low value, you might get an undetermined case. But in this case, the undetermined case can't even happen because of the range of the input voltage you're applying, because of what we're applying from the VMID. Take it through a little bit. But it's tricky. I said this was the trickiest question of all. That part I thought was the hardest of the whole exam, and that has actually shown that way as well. But based on that, now I can go to my next gate, and again has a very similar characteristic. But now the VM is switched a little bit as a result of the ratio of your devices and the overall voltage range you have. Instead of going to 1.2 volt, I'm going to 1 volt only. So the first gate went to 1.2 volt. This one loses 0.2 at both ends. So my midpoint is 0.6. But the bottom line, if I combine the two together now, I'm multiplying with each other, I get this characteristic. Right? So the trick part was really that 0.2 volt loss at both ends. This is actually something that people use in practice. If I want to have a gate that has a reduced swing, I want to save power. I don't want to swing all the way from rail to rail. I can easily take a threshold off from both the top end and the bottom end by putting those devices there. So this is actually used in practical circuits. It's not really something that we came up with to make life miserable for you. Okay? And then there's some power equations. This is fairly straightforward. Once you know how it switches, what the extreme voltages are, you can basically determine how much power is consumed in each of those cases. So I just would recommend that you look through the solutions. And again, we're going to go briefly to this during discussion sessions as well. If you have any questions, please come by during office hours or for basically the discussion sessions. Bottom line of all this is, if I go back now to here, this is where we are at. So if you combine it all together, great. I'm going to return the exams at the end of the lecture. The total was not 39. The mean is 25.85, median 26.25, which is quite good for an exam, I think. Typically, this is where, if I look at my midterms of the past, this actually is a nice number. I've had worse. Standard deviation 6.54, max is 37 out of the 39. So, and I was planning to put the distribution. I'm going to put these things in AP Bears or in B space as soon as possible. I put them in a spreadsheet right now, but I'm going to put them in B space as well. And I'm going to try to plot out the distribution. We just graded yesterday night, so didn't have the chance yet to kind of figure out how the distribution looked like. But as far as I'm concerned, it looked like a very nice distribution. Actually, with a lot of people sitting around that 26-point range, 25-point range is where the majority of you are. Okay? Any questions? So check it through. I'll return them at the end of the lecture. Please, if you see anything that's wrong in our grading, which might happen, we don't always add up correctly, even though we check it a couple of times, or anything like that, let us know. But please do so within a week. So you can come up to Wednesday evening next week. I'll still accept changes and things like that, modification. But after that, I consider it final. I don't want to keep on going back and things like that within months and so. So that's that. That's the midterm. All right. Let's talk a little bit about projects. Okay, so what I basically mentioned to you before, what we're going to do is something I dubbed, I came up with it. It's kind of an approximation, but I call it a neural associative memory. Now, it doesn't mean very much, but it will mean a lot to you in a couple of weeks. And definitely by the end of the semester, you basically will hate it. But, no, actually, I think you'll love it. You think it's going to be great fun. So let me first explain you a little bit about what the difference is and why I call it a neural associative memory. So what is a memory? A typical SRAM, let's say SRAM is a static random access memory. What happens in a memory is that, if I go here, take a blind. A memory is something of this nature, is that somewhere I have an array of data organized as rows, and I have an address which I send to a decoder, as we already discussed before, and you pick one of those rows, and out comes the data. That's the read operation. By the way, in this project, we're never going to think about writing into the memory. We assume that the data is in the memory, and that somebody wrote it there magically. So don't worry about how the data gets in there, how you write data into the structure. That's not an issue. You're just going to look at read operators. So typical a memory gives you is a certain amount X, which are data, which is a function of your address Y. Okay? Y has a width of K. The number of words that you have in your memory is going to be 2 to the power K, right? And we call that N. So you have 10 address bits, I have 1,000 rows in my memory. And the width of the word that comes out of there is going to be equal to M. This is like 16-bit words or whatever I've stored in my memory. So typical memory operation, you apply an address, or memory read operation, you apply an address, you get a data word out. Okay? So that's the way 99.99 of the memories work. But now here's another interesting thing you can assume. Suppose I have a memory, but instead of applying an address, I apply the data. I apply a data word, any data word, and the output is going to be the address of where that data might be stored in your memory. It's the opposite. You apply the data and say, if that data is stored somewhere in the memory, tell me where it is. Okay? One application where this comes in quite handily is when you have, for instance, caches. Caches in microprocessors on a chip. When you want to do a cache, you say, have already seen that instruction. You apply the instruction and you find out, oh, it's right there. It's in my cache. A very simple example. That's what we call an associative memory. Associative memory is you apply the data here. Now it's the opposite direction. And out of this comes the address on the other side. So it's kind of reversing everything. Still, we don't do any writing. The data is all basically reading. So that's nice. But what it requires is that the way you can imagine is that you apply the data and you compare it with all the data that's stored in memory. And if you have a match, if they are identical to each other, you raise this line here. So there might be 1, 0, and all the other ones, 1, 1, and all the ones 0. That's where you have the match. And then you translate this into an address. Right? Instead of an encoder, decoder, you have an encoder. It goes from 2 to the end to K. oh sorry, from 2 to the k bits. So this only works when you have a perfect match. All the bits are exactly the same. In this project, we're going to do something a little bit different. So, well, I'm not even, suppose I take a data word, a certain value, 42. I'm not really interested if I would find 42 into that memory, that would be cool. But maybe there is no 42. There might be 45. And that's good enough. I'm going to look for the data words that's the closest to the word I'm looking for. So you won't have a perfect match, but you are going to compute a distance between what you apply and every word in the memory. And the one with the smallest distance is the one you're going to select. So it's an approximate associative memory. Now, so that's the whole idea. It's very similar to an associative memory, but it's going to take a lot more arithmetic. Because if you think about it, in associative memory, what you have to do is just a comparison. Here, I have to do a distance computation, and I have to compute a minimum inside the memory array. Okay, so let's go back to the slides here. Okay, so that's what our associative neural memory is. It's a memory that when you apply the data, it returns the address for which the data is the closest match to the applied data. Now, why do I call it neural? Well, there's a whole theory in the neuroscience that claims that a lot of the classification things are done. A lot of things your brain is really good at is to do pattern matching, to do classification, to do recognition. You see something, you recognize it, even though it might not be exactly the same as what you've seen before. So there's a lot of kind of classification functionality going on. Now that's the same thing with the smell or with a whole bunch of sensory functions. You try to do a matching, but it's not a matching to the thing that's exactly the same. So this is how, for instance, the eye works, and here's how the nose works. The nose has a whole bunch of sensors, actually lots of them. In your nose, there's a couple of million sensors out there that can basically sniff out particular molecules. Actually, they're not very good sensors, it's kind of lousy sensors, because every sensor it will be finding a couple of molecules, not a single one. And they overlap. And you have lots of them and they're redundant. So you have lots of sensors getting all that information, and they're going to give you a certain analog signal. I have a good signal here, or I have no match, and so on and so forth. A lot of redundancy. The first thing the nose is going to do within the what's called the olfactory system is reduce that information. Because there's so much redundancy, you're going to combine all those different sensors together. If they're all the same, you wire them together and you get a stronger signal. So there's some automatic gain control and stuff like that going in. But then, still, you're working with signals that are typically extremely noisy, small, not very distinctive. Let's say if I smell something, typically you won't smell one single molecule, but you have a variety of molecules. Some of them might be lots of them, some of them might just have a few of them. And very often, I can even pick out that few number. In the presence of quite a bit of molecules of one type, I still can figure out, hey, there's something extra in there. Definitely when you smell wine or something like that. People are really good in that, in trying to figure out 5, 6, 7 different smells in there. The way the neural system does this is what's by a thing which is called over completeness. They're going to map it from a small, this is a reduced number, they're going to map it into a hugely over-dimensioned space. Randomly. They just project it in many random, so you get some clustering effect. But the bottom line is you have this huge representation which is actually happening at the, when you go from the nose into the cortex, into the brain, that's really where this expansion happens. Huge expansion to many different regions of the brain. But the last phase is really where the associative memories phase happens, where you start taking those patterns and try to map against stored patterns. And again, it's not against exactly the same thing, it is something that might be similar. You compute distances and you figure out which one is the best match. So this whole associative memory that we're talking is really where we do pattern storage and retrieval is the last phase, and that's really what happens in the cortex. Cortex is this little top layer of the brain, very thin, about 2 millimeters thick, but huge. It's like a big towel. You kind of fold it all together. That's where those things are basically sitting in. So it's interesting. The question is, could we build something like that in silicon? And that's what we're going to try to see. And you will see it's not as easy because there's a lot of functions in there. All right. So here's what we're going to do. Suppose I'm giving you, this is the functional definition, given a vector xn of integers. So we have a memory stored, basically a vector. Xn is the number of words in my memory. Stored in an SRAM memory, and each of words is m bits wide. Okay, so you have a memory of size n times m. That SRAM type of design. So what I would like to do for an input y is a data word with width m again. We want to find the value of I. I is the address, for which holds that the distance between y and xi is minimum. And the way I define the distance is quite simple. I take the value of y, I subtract what's stored at position I, so it's value xi, subtract them, and take the absolute value. And you're going to try to find the minimum value of that, and for that we're going to basically return the I value. That's the output. So think about it, what you have to do. Basic things is that I'm going to apply an input word into my memory, and for each word I'm going to compute that distance, which is a subtraction followed by an absolute value computation. Once I've done that, I'm now going to try to compute the minimum over all those values, and for that I'm going to return the I. Okay? Now, we would like to do, yes?
If m is like big and then everything's selected randomly, wouldn't we expect a lot of overlap in the number of minimum distances?
No, suppose these are all kind of signed integer numbers. Right? So look at your whole memory space as signed. So there are words, let's say I have 10 bits. I have numbers from 0 or minus 1023 to 1024, approximately. No, actually it's less. You get, it's only half of it. It's minus 511 to 512. That's the range of numbers you have. So you have 1,000 numbers stored, and in this case, 10 bits or whatever, 9 bits. That's the range of things you have. So obviously, if you would have a large memory, which is where the size of the memory is way larger than the number of representations you have, you will have many matches. Right? You would have numbers of times the same number. But typically, that's not what you're going to assume. Typically, have a sparse representation.
No, I mean in terms of the distance. You know what I mean? Because like if you put in like 999,
Right.
right, you get a match for 1,998.
That's right. That's 2.
Right, but I mean then you like walk down the line 2, 4, 8.
No. So if you have 999, and I apply 999, you might have 2 numbers that are equal distance on both ends, right? So the number of matches, if your representation is sparse, the number of words that are going to be close to where you are is actually going to be fairly limited. And that's in generally the case. Obviously, if I would make the width of my memory way larger compared to the number of words I have, I will have too many matches. So the rule that I'm giving you, and that actually you will read the project definition. The rule I'm giving you, if you have 2 matches, or if you have a number of words that are equal distance, pick any one of those, the one you like the best, from a computational perspective, because it doesn't matter. They're equal distance, so any one of them is good. But typically, I will assume that's going to be fairly small. Now, the goal here is primarily going to be, we're going to start with something to think about it has to be area efficient. You can really blow this up, if you can imagine, right? So I have a huge memory. If I bring all those words out to the side here, it's going to have tons of wires. And if I do this not in a very structured fashion, this whole thing is going to blow up. So I want to do this in such a way that it's going to be regular, and very repetitive. I want to have a structure which is very simple. Actually, in reality, you're going to design 2 cells, 2 gates, 2 logic blocks. That's it. Independent of the size of the memory. I don't want you to design every cell differently. They should be all the same. So 2 cells is all you're going to have to design by the end of the semester. They're going to be complex. Be not mistaken. There's going to be quite a bit of gates in there. But 2 cells is all you're allowed to do. So if you look at your memory array, it's an array of cells. Each of the cells should be the same. And it's going to have a memory cell in there plus a bunch of logic. And now you're going to have what's called on the side here an encoder, which is going to take some data words coming out here like we had for the associative memory and compute the value of the address, the best match. So again, you want to have something that's nicely structured and fits beautifully together from an area perspective. So 2 cells, one here, that's all you're going to design. So area is going to be important. Later on, when we do circuit optimization, we're going to be worrying a little bit about energy. But right now, forget about energy. We're just going to make sure that it gets the right function. So step 1 is going to be logic design. Design me something that basically can fit within, does the right computations. How would you define the logic per cell, and how would you size the transistor in such a way that I get a decent delay? So we're going to do logical effort analysis, and you're going to size it in such a way to get optimal delay. But the logic and design itself is already going to be an interesting challenge. Because think about it. Here's what I have. Here's my memory array. So I have n words, each of them storing a value of x. In our project, it's going to be 1024, 10 bits of address. This is going to be 16-bit bytes. So the data word is 16. So 16 times 1024 memory array. That's really what we're looking at. So I apply my value y, which is going to be the same width as your memory array. So what you do is like in any memory, you're going to feed this through vertical wires to each of the cells. So the same value y goes up vertically, and you present it to every cell in the memory array. To give you a little bit more perspective, I'm going to talk about memory structures in one of the next lectures to give you an idea how you do this in memories. But bottom line, you can imagine that I broadcast the same value of y to every cell or every row in the memory. Then in every row, I'm going to compute the distance what I have stored there. I'm going to take xi and subtract from that y. So you do xy minus y, and you do this in every row simultaneously. So I apply all my words, and simultaneously, I'm reading out I basically do all the subtractions together. Absolute value, that's a little bit tricky. What you do for an absolute value, again, I'm going to talk about this in about a lecture or so. Absolute value is, if I know the sign, if I take a data word, I look at the sign, that's the most significant bit if you use 2's complement, I can use that to flip the bits around. If it's positive, if the sign is 0, it means a positive word. I don't do anything. If it's 1, I flip all the bits around. So absolute value, that's not that hard to do. We know how to do that. So you have that distance, but now you have to do the minimum. That's where the challenge is going to lie. How do you compute simultaneously the minimum of 1024 words? I can build a giant block that has 1024 inputs, and out of this comes the minimum value. That's not the way you're going to do that. That would be a disaster. You can imagine, right? You have to bring all those words out. You have to have this giant block. You have about 1024 times 16 bits wires. So that's 16,000 wires going in there. And suddenly 24 bits comes out with the minimum value. You don't want to do that. The way you're going to do this is by iteration. For instance, if I start at the top, there's no minimum there yet. I'm the first word. I'm going to take the value of the first word. I'm going to compute its minimum. Well, it's easy. It's the word itself, the distance itself. I pass this on to the next row. The next row sees that minimum, and it has its own distance. It compares the two. If its own minimum is smaller, it says, okay, I'm the winner, and it passes on its result to the next row and says, hey, by the way, I was the winner. You raise a bit at the output that says, I was winner. And you move this forward. So you move this all the way down to the bottom. So you have a large logical chain from the top to the bottom. Minimum, 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 minimum. These are multiplexers, by the way. It's not hard. So all the way to the bottom. And on the side here, you're going to have now a number of winners. And as I said, ultimately, the one that's going to be the winner is the one at the bottom that has, say, I was the last winner. You want to find that? That's the address you want to put out. So that's kind of the approach you should use. It's going to give you the best possible or the most efficient implementation. It's going to be a giant ripple structure. It's not going to be fast. It's actually going to be slow as hell. But that's okay. We're not into speed here. The brain doesn't work that fast. Brain is actually quite slow. But you have lots of things happening simultaneously. So that's kind of the idea. And as I said, what we're going to look at is primarily, in this round, logical design, basic functionality, maybe do some thinking about how to make it a bit faster, and then do logical effort sizing of your device in such a way that you minimize the delay. Okay? So, key roles, explore logic design and architectural options. That's what you're going to do first. Trying to figure out what are the equations for. Write down the logical expression. As I said, make sure that you don't get tons of wires coming out. Use regularity. Regular structures are going to be very important. That's going to give you the best possible result from an area perspective, but also from a power and performance perspective. So then we want to do first order delay and energy computation. Energy computation I might actually even drop in the first round. We're still not 100% sure, but actually I was wrong on the numbers here. The numbers were n is equal 128 and m is 16. Okay? So we can see that we have a very large space. Actually, the chances that you're going to have two matches is actually quite small, because the number of words stored in the memory is actually quite small. And note, if two values have equal minimum distances, choose any one that you feel the best about. And it's going to be purely driven by how your computational structure works. How make it simple from a computational side. Okay? Any questions on that? Is that clear? Yes?
And then n is the number of words?
N is the number of words. So 128 words, so it's an 8, that's a 7-bit memory, 7-bit address. So the output is going to be 7 bits wide. And m is 16, so 16, that's 2 to the 16, that's 4,000 possible values. I have only 128 words in my memory, so the chance that you're going to have a lot of matches are quite small in this particular case. Other questions? So, by the way, only complementary CMOS for the time being. Don't do funny things like bipolar design or gallium arsenide or anything like that. It's only silicon. No dynamic logic. So just stick to the basics. Don't try to be too clever at this point in time. It's already going to be quite a bit of fun to start with. Okay? All right, so yes.
Project teams work?
Okay, so, oh, yes, good questions. How do teams work? You have to choose a partner, groups of 2. If you feel out you want to do it with a group of 3, you say, well, I really want to be with 3 people, then I'll figure out something that you have to do more work. It's only fair. If you cannot find a partner, let me know. Use BSpace to find partners, or Piazza, work around it. Basically, we have all the mechanisms to it. But I really think that's the best thing to do is groups of 2. The phases are going to be such that we're going to give you a couple of weeks, about let me see, probably by about spring break or something like that. We should have phase 1. Phase 2 is going to be the same thing, but we're going to do real circuit design. In phase 2, you're going to have to translate this from gates into circuits and do optimization. And I said, then I'm going to start worrying about energy. First phase, forget about it, not too much energy. Second phase, circuit design. Last phase, we're going to do layout. I want to actually be seeing this thing and how efficient you can make it. It's not going to be pretty. You have a memory cell and a lot of logic into your block. because it's you're going to have adder, at least 2 adder cells. There's going to be some other multiplexers in there. There might be a comparator, all depending on how you designed your logic. But there's a lot of things you can play around with. Write down the Boolean expressions and start manipulating them, because you will see there's some interesting things you can do. It's a fairly rich problem, so it's going to give you some opportunity for creativity. Okay? Any other questions? Yes?
Maybe you'll go over this later, but are we free to choose which binary representation do you want?
Yeah. If you want to do gray coding or something like that, that's on the end. Yeah, you could basically use something which is a different number system if you want to. Yeah, no, I'll give you some freedom in there. I'm not going to restrain it. If you find a way to get energy more efficient by having less bits flipping around, things like that, so all those things are possibilities. But yeah, as I said, I'm not going to, don't go venture on the wild side with respect to voltage and with logic styles and things like that. But remember, phase 1 primarily is going to be about speed. And why I say, well, I don't care too much about speed, but think about it later. What we're going to do in phase 2 is energy. Right? Where are the biggest energy savings coming from? Reducing the supply voltage. If I will tell you now this thing, in phase 2 I'll tell you this logic of yours has to work within this time. I'm going to give you a maximum amount of time. If you have something that already was faster, you can trade it off for energy. You can slow down your logic by reducing the supply voltage and get a gain in energy. So that's why in phase 1, it says, think about simplicity and then optimize logical effort and logical structure in such a way that you get the fastest possible implementation. Okay? So speed is number 1 in the first phase. But you will see it's not easy, because you have, if you look at that minimum computation, it's a long ripple. And ripples basically means that you're going to go to many gates. Okay? All right, I'll see you on Friday. Oh, we can hand out the midterms. Shouldn't forget that. So I'm just going to call them off alphabet.